All right, if you guys took a look at those videos that I sent you, you should have seen a number of videos on basically on gravity. And what two of the videos depicted was objects that would fall with no air resistance at all. So in one of them, they're on the moon, they're dropping a feather and a hammer. Obviously, one that we would normally expect to hit the ground before the other, but you see on the moon that they hit at exactly the same time. And then they accomplished the same exact thing in that NASA facility where they were able to remove all the air from the room. So, and in that case, they did a bowling ball, and then they also did a feather. So what you're going to see is that even with air, we can still make that happen. So if I take two identical objects here, they're pretty much identical in their composition, their shape. They're both hollow inside. The only thing that's different is obviously this one's much larger than this. But if you take a look here, despite the fact that this one's much larger, what we're going to see is that, and you can listen with your ears too, they should be at the same vertical position each instant in time. And then when you hear with your ears, you're only going to hear one bounce because they're hitting the ground at exactly the same time. So that extreme disparity in size doesn't really seem to be affecting when this is going to hit the ground. Now I can take something of a different shape here, my marker here, and the ball, and if I release them at the exact same time, we're still not going to see any difference there. Essentially, you're still going to see them falling in unison with each other as they travel down. Once you get into a shape where something's very light and not really aerodynamic, then you're not going to see them hit the ground at the same time. You're going to see this one take a lot longer to do so. It's not going to fall down at the same rate. So for the most part, objects that we deal with, we're going to try to focus on objects where we can ignore the air resistance. So we'll think about that in the, I would say, the coming days. But what we want to talk about is the acceleration due to gravity. That last video clip I sent you was a guy who literally goes to the top of the stratosphere in a big gigantic helium balloon, and he just jumps from the top of the stratosphere all the way down, not to the ground, but he ends up having to deploy a parachute. And what you really want to take a look at in that video clip and pay attention to is how fast he travels down, how fast he goes out of view, how fast he gains speed, because gravity is that strong. Gravity causes things to accelerate pretty quickly. And if we wanted to quantify the acceleration due to gravity, the A value is equal to, we're going to say, negative G. And G is a physical constant in this class. G is equal to 9.81 meters per second squared. Now, the reason that there's a negative sign there is because when I drop something, it accelerates down. Gravity is going to pull it down. So our acceleration due to gravity is downward. Gravity accelerates downward. So that's why we have that sign there. Now, what that means is that basically the acceleration due to gravity is equal to negative 9.81 meters per second squared. Now, let's try to put that in perspective. This isn't going to be in the air for a second, but that guy definitely was. And as it drops, it picks up speed all along the way. And the further and further it drops, the more and more speed it's going to pick up. Everybody that's jumping from an elevated position intuitively knows there's a limit as to how high you're willing to jump from, because you'll hit the ground harder and harder the higher you jump from. So essentially, the way this works is this. Every single second that goes by, we're going to gain a hair under 10 meters per second, which is about 20 miles per hour. So in 1 second, you're probably going almost 20 miles per hour. In 2 seconds, you'll be going 20 meters per second or close to it, and you'll be going 40 miles per hour. That means in 5 seconds, you'll pick up enough speed to be going approximately 100 miles per hour if you are in free fall. Now, that would actually require a lot of distance to get to that point, but it definitely is possible. And that's what we're going to end up looking at in the next video. Last thing I want to show to you is the kinematic formulas that we're going to use. We want to use those for horizontal motion, and we're going to modify these slightly for vertical motion. So if we rewrite the formulas that we learned in kinematics, those formulas are, first one was delta x equals 1/2 vi plus vf times time. Second formula was vf equals vi plus at. Third formula delta x equals VIT plus 1/2 AT squared. Last formula, VF squared equals VI squared plus 2A delta x. We're going to modify those slightly because the x direction is this direction, the horizontal direction. And we want to look at a problem where we're looking at the y direction. So what we're going to do is instead of x's, we'll use y's. Because if we're dropping something from, let's say, an elevated position, this could be our initial position and it can go downwards, and this could be our final position. And delta y would equal final position minus initial position. That would be our displacement, if you will. So we'll use y's instead of x's. And then the last thing that we're going to do is, since we know that gravity is what's going to be influencing the acceleration here, we're going to use the acceleration due to gravity as our known acceleration in these formulas here. So we're going to modify the formulas by replacing the x's with y's and the a's with a negative g. So if we do that, let's take a look. I'll write out the first formula, but this is actually seldom used in gravity. It'd be delta y now equals 1/2 VI plus VF times T. The next one would be VF equals VI plus, we're going to substitute in negative G into there, times time. Next one after that, delta Y, change that, VIT 1/2 plus 1/2. Negative G, notice I'm writing it in parentheses here, T squared. And then the last formula is going to be VF squared equals VI squared plus 2. In for A, I write negative G, and in for delta X, I write delta Y. So they are the same exact formulas, it's just that we've modified them ever so slightly. So why don't you write these four formulas down. We're probably only going to use the last three, and then what we'll do is we'll take a look at a hypothetical problem involving gravity, and we'll have you guys solve for a few things and see what you end up getting.